There are some ideas in math that just feel a little off, right? They seem to go against the rules we thought we knew. Today, we're going to calmly unpack one of the most common ones, and I think you'll find that the logic behind it is actually surprisingly beautiful. So here's the puzzle we're going to tackle. This simple statement: 0 factorial equals 1. Now, if you've ever looked at that and just thought, wait a minute, that can't be right, you're definitely not alone. It seems to fly in the face of our intuition.
And yeah, that's exactly where the confusion comes from. I mean, the whole definition of a factorial seems to fall apart here. Your line of thinking is perfectly logical, but it turns out we just need to look at this from a slightly different angle. And don't worry, it'll all start to make sense as we walk through it.
All right, so first things first, let's make sure we're all on the same page about what a factorial even is. Okay, so a factorial, the thing with the exclamation point, it just means you multiply a number by every positive whole number smaller than it. So 4 factorial or 4 factorial is just 4 times 3 times 2 times 1, which is 24. Easy enough. But that still doesn't really help us figure out what to do with 0. So to get to the bottom of this, we're actually going to take a little detour. We're going to look at a pattern that you're already very familiar with to find a hidden clue.
We're going to look at something we all know pretty well: powers, or exponents. The way they behave holds the secret to understanding 0 factorial. Because just like with factorials, the simple definition of what a power is kind of breaks down when you get to 0. But the pattern holds up.
All right, let's just run through a quick pattern. We'll start with something we all know. 2 to the power of 3 is 8. And 2 to the power of 2, well, that's 4. Simple, predictable. And 2 to the power of 1 is, of course, 2. Now, we're used to going forward with these, right? But what happens if we try to go backwards? Okay, so here's where it gets interesting. As the power goes down by 1, what are we actually doing to the result? Well, to get from 8 down to 4, we just divide by 2. To get from 4 down to 2, we divide by 2 again. See the pattern? It's perfectly consistent. So to find 2 to the power of 0, we just follow that pattern one more time. We take 2 and we divide by 2, which gives us 1. And that right there, that's the key. This whole idea of working backwards, of just following a pattern that's already been established, it's a huge part of how math stays so consistent. And this will all connect in just a moment. Okay, so now that we have this new tool, this idea of working backwards, let's bring it back to our original problem with factorials. Let's build our factorial sequence again, starting from the top. 4 factorial, like we said, is 24. Moving down, 3 factorial is 3 times 2 times 1, which gives us 6. 2 factorial is just 2 times 1, so that's 2. And 1 factorial is, well, it's just 1. Okay, so now we're right at the edge of our puzzle. What comes next? Well, let's just follow the pattern backwards. All right, let's do the exact same thing we did before. To get from 4 factorial down to 3 factorial, we divide 24 by 4 and we get 6. To get from 3 factorial down to 2 factorial, we divide 6 by 3 and we get 2. From 2 factorial to 1 factorial, we divide 2 by 2 and we get 1. The pattern is crystal clear. So to take that final step from 1 factorial down to 0 factorial, we have to continue the pattern. We have to divide by 1.
And 1 divided by 1 is 1. And there you have it. It's not some random rule somebody made up. It's the only answer that possibly works if you want to keep the logical, beautiful pattern of mathematics intact.
Just let that sink in for a second. It's a real shift from seeing math as a bunch of rules you have to memorize to seeing it as this elegant system of consistent patterns. If you'd like to share, I'd honestly be curious to read in the comments about any other math patterns that you've always found kind of fascinating. This points to something much, much bigger. Why is it so important to mathematicians to keep these patterns consistent in the first place? The thing is, math is kind of like this whole imagined world, built on one simple promise: consistency. Its real power isn't just that it helps us solve problems, but that its rules are always, always reliable. And once you have a foundation that solid, you can build some truly incredible things on top of it. And believe me, this isn't just some abstract philosophical thing. This deep commitment to following a pattern, sometimes just for the sake of curiosity, has led to discoveries that have completely changed our world. I mean, take this mathematician, Fourier, for example. He was just playing around with a pattern he thought was interesting. This idea that any complicated wave could be built by just adding up a bunch of simple waves. He wasn't trying to invent anything practical. He was just
Curious. And yet today, that very same idea is the foundation of our entire digital world. Turn the signals into the music we listen to and the pictures we see. So you see, 0 factorial equaling 1, it isn't just some random, quirky math fact. It's a little peek into the very soul of mathematics itself, a world built on the beauty of consistent patterns. Which kind of makes you wonder, what's the next beautiful pattern out there, just waiting to be discovered?